Okay, welcome everyone to this Pegasor webinar. Today we will talk about ultrafine particle monitoring and specifically real-time ultrafine particle monitoring. My name is Henna Isherwood. I am in charge of sales and marketing here at Pegasor. And today I will give this presentation together with my colleague, Dr. Erkka Saukko, who is in charge of technology and product development here at Pegasor. So let's see. We will start today's webinar with just a short introduction to Pegasor, who we are and what is it that we do as a company. As mentioned, our presentation today will focus on ultrafine particles, where they come from, what they are, and why they should be monitored. And then after my part of this presentation, I will give the stage to my colleague, Dr. Saukko, who will then explain more about the Pegasor technologies, sensors, and monitors for ultrafine particle monitoring. Now we have the Q&A section should be enabled in this event, as is the chat function in case you have any questions. Pegasor company is, we are a Finnish company. We are based in Tampere. We focus on environmental technologies. Company was founded in year 2008, so 3 years more, and we'll be celebrating our 20th anniversary. Since a couple of years now, Pegasor company has been part of a French organization called Capelec Group. They are specialized in instrumentation and equipment for PTI testing of vehicles. We here at Pegasor, we focus on nanoparticle and ultrafine particle technologies for different applications. One application being this PTI testing measurements, but we have lots of activities in other ultrafine particle application areas as well. We develop our own technologies for the detection. All Pegasor sensors and monitors and instruments are based on Pegasor patented own electrical detection technologies. Erkka will talk a little bit more about that later on in the presentation. We have different instruments for different measurement application areas, and everything is designed here in our main offices in Tampere. We do have global partner network around the world. We have several partners in Europe, Asia, North and South America. The different areas where we currently operate in include emission monitoring measurements, so detecting exhaust emissions and from vehicles, and then also stack emissions from, for example, energy production plants. And typically in these application areas, the sample is hot, so the measurement of the particles is a little bit more complicated than in maybe air quality monitoring, which is the second main application area where our instruments and sensors are used. For example, outdoor air monitoring, urban city areas, fence line monitoring near industrial plants and so on. But also in indoor areas, we have instrumentation and technologies for occupational health and safety monitoring, or for example, adjustment of ventilation systems and such. Currently, we have 3 different standalone instruments that are based on Pegasor sensor technology. In our product line, we have the Pegasor particle counter available for emission monitoring, Pegasor Airam, which is the focus of today's presentation. This is for outdoor air measurements, and then the Airin device, which is more for indoor air quality monitoring. All of these instruments, they are designed for measuring ultrafine particles. This is our core competence and know-how, and this is what our instruments measure. Ultrafine particles are typically classified as particles that are larger of 10 nanometers in size. Typically in here we have a picture of a typical particle size distribution in an urban area. We have two different graphs presented in here. We have the particle mass size distribution in the black curve and particle number size distribution in the red curve. And as we can see, typically in urban areas, the particle mass size distribution is dominated by the larger particles. Up to about 10 micron is typically the regulations that are used to define acceptable particle levels in urban areas. Typical quantities that are monitored are PM10 and PM2.5. That is particle mass of particles smaller than 10 micrometers and 2.5 micrometers respectively. However, typically, especially in urban areas, if you look at the number concentration of particles, that can be dominated massively by the ultrafine particles, the smaller particles that are typically less than about 100 nanometers in size. And this is our focus today. These smaller particles that are typically quite abundant in urban areas especially. So why do these ultrafine particles matter then? As most of you probably are aware, there are several studies published about the health effects of ultrafine particles. They are often considered more harmful for human health than the larger particles because the larger particles typically can stay in your mouth or throat area. For example, sand can be very irritating as an experience, but it may not be so harmful to your health as the smaller particles that can go deep into your lungs. There have even been studies that these ultrafine particles can go from your lungs into your bloodstream and into different organs and even brain, and can cause all kinds of different health problems from asthma to even Alzheimer's. So the health effects are critical, and there's much more awareness nowadays about the health implications of these fine particles. Here are just a few news articles I found yesterday from Google News, checking recent news articles about ultrafine particles, and several studies were there from links between ultrafine particle concentrations and deaths in certain areas to ultrafine particles having effect into gene function on a cellular level in humans. So lots of publicity on this topic nowadays, and not just on the news side, but also on the regulation side. We'll come back to that next. Ultrafine particles in urban areas, especially, they can come from various different sources. There are, of course, the human-made particles, let's say, from anthropogenic sources, typically combustion-generated particles. So traffic is typically considered one of the main sources of ultrafine particles in city areas especially, but also different industries and energy production, steel plants, and so on. In indoor areas, then you can have, depending, of course, on the area where you are, you can have, for example, candle smoke, cooking emissions, smoking, vaping, that can contribute massively to the levels of these small particles in the air. Besides the anthropogenic sources, we can also have natural sources of the particles. So again, combustion sources, for example, forest fires, can cause big levels, localized levels of ultrafine particles. Then, for example, volcanic eruptions can be a source of these. And in sea or ocean areas, you can have particles coming from the sea spray, from the ocean, and so on. The other important factor where there has been a lot of research, especially aerosol research, is secondary aerosol formation. So these small particles not only come directly from these processes, for example, combustion, but they can also be formed in the atmosphere from the gases and gaseous compounds, for example, volatile organic compounds, depending on the different conditions in the atmosphere, including amount of sunlight and humidity and temperature and so on. So very many different sources, some that can be controlled more easily by humans and some not. But nevertheless, some regulations are now already coming in this field. World Health Organization published a couple of years ago the Global Air Quality Guidelines, and now for the first time they have mentioned good practice statements on ultrafine particles, and the aim is to guide national and regional authorities and research towards measures to reduce ambient ultrafine particle concentrations. This global air quality guideline defines what is the quantity that should be measured, that is the particle number concentration of ultrafine particles that are defined as particles larger than 10 nanometers in size, how they should be monitored, and what are the recommended levels that should be reached. Now, based on the WHO guidelines, the EU has published end of last year the new version of the Air Quality Directive. This is largely based on the World Health Organization guidelines, and member states have until end of next year to transpose this directive into local legislations. The EU Air Quality Directive has an ambitious goal of zero pollution by 2050. And the new requirements in this directive have several new pollutants that need to be monitored. And one of them is now, that is mentioned for the first time, is ultrafine particles. Here is a link to the directive, and there's also a link in Pegasor website to this, if you're interested in more detail. So there is interest and knowledge about the effects of the ultrafine particles and new regulations that are set in place that require monitoring of ultrafine particles, and this is a little bit more challenging than what have previously been measured when it comes to particle levels in atmosphere. The ultrafine particle instrumentation used in ultrafine particle monitoring is usually quite specialized because the particle size that we need to detect is really small. Definition is larger than 10 nanometers in size. The quantity that we need to measure now is particle number concentration instead of the mass that has been traditionally the quantity that has been monitored in air quality measurements. And in addition, the instrument should have quite dynamic concentration range since the concentrations of the UFPs can vary quite largely, even in one city area from very low levels to very high concentrations, and they can vary very quickly. So real-time data is preferred when these ultrafine particles are monitored. And this is, of course, something where Pegasor has expertise for over 20 years now. Real-time sensor and instrument technologies for ultrafine particles. And on that note, I will hand the stage to Erkka.
Thanks. So it's a good spot to continue with the technology and equipment that we offer. Let's see if I get, okay, here, our presentation technology going. So first I'd like to introduce our Pegasor particle sensor PPS G2. So this is our second generation ultrafine particle sensor. It's based on electrical detection of particles, and it's well suited to any real-time particle measurement tasks. Its core design principles were to make this simple to operate and set up. We built it to have a robust structure, and this can be heated up to 200 degrees C for demanding applications like the PTI or other combustion or emission measurements. The principle of operation is shown here. We have particles are drawn into the sensor or the measurement section here with an ejector pump, and this pump is driven by clean air that is ionized in this diffusion charger or corona charger. So we have clean air going at high velocity through a small nozzle, and this drives the ejector that brings in the particles. The particles or the sample is mixed with this ionized air, so the particles collect the charge in the ions in the air, and so the particles are charged, and any excess ions are then captured in an ion trap. So it's an electrostatic trap structure that has a potential difference, electrical potential between the walls of the cavity. So ions move quickly in this area due to the electric field, and since they're very small, they move quickly, and these particles, they carry a few charges, few electrical charges, but they are much larger than ions, so they move very slowly, so they are not captured in this section. So the end result is that our particles carry a charge and they exit out of the sensor. And that's the core principle behind escaping charge measurement. So we measure the current that is being induced into the sensor by these particles that carry these ions. So it's an electric current that we measure. The benefit here is that since we do electrical measurement, we have very wide concentration range that we are capable of measuring, and we are not collecting the particles. We use some of this clean air to protect critical insulators in here so that we can measure these very low currents. So at the lower limit of detection, we are measuring femtoampere level currents. But our electrometer is not even near of this part where the sample is processed. So we have at the same time the benefit of very robust measurement where we do not collect the sample, so contamination is very low, but at the same time we can have very sensitive measurement because our electronics can be kept separate, or the measurement element itself is in a cool and stable environment. So electrically, this looks like this. We have sample going into this internal Faraday cage where we have the particle processing, so charging and removal of excess ions, and the sample goes out. And what we measure is that the sensitive electrometer keeps these two Faraday cages at equilibrium, so we actually have the same charge or current measured here at the electrometer that is taken out of the sensor by these escaping particles. The benefit here is that we have a very stable system. The particles are charged and the trap operates even at high temperature, so we don't have any condensation. But the electrometer is in a cool, stable condition, and the sensitivity and all the calibrations are based on passive components, so it's very stable over a long time period. Structurally, it's a very simple flow through operation. So we have sample going in, then we have a heater system that, depending on application, either takes out just the water vapor or water from droplets, so we are left with the core particle inside, or in high temperature applications, we can remove all the volatile components so that only soot is left on the of the particles. So this is required for emission measurements. Then we do the actual measurement, and the sample is thrown out of the sensor. So it's in its core principle, it's very easy and it's very simple. We have all the sample treatment and the measurement in the same package, which is kept at high temperature, so we reduce risk of condensation and contamination here. Structurally, just a couple of details. We have packed this with all the necessary details or parts that are needed. So we have the ion source and the ejector pump. The trap injection section is folded like this, so it's maximizes the efficiency. And the VPR, or the heat particle processing section, or the heating section, is quite compact, and it takes care of the thermal management of the whole sensor. And since everything is now that is needed for particle measurement is integrated into this one sensor, it's pretty easy to build OEM products out of this. So the sensor provides the measurement of the particle number, or the particle surface area, or the ultrafine particle mass, given that we have an estimate of the density. Then we have particle size estimation, which is often very interesting for our customers. It provides sample pumping, and there's the volatile particle remover, which can be also used as a dehumidifier for ambient applications. We have thermal insulation to keep temperatures down in the enclosure, and there's a heater for the VPR. We have extensive diagnostics inside to monitor the pumping air temperature, relative humidity, and pressure, so we know that everything is fine on the pumping side. We get ambient pressure measurement, and then we also have a thermocouple outlet for the temperature control here. All the internal functions are monitored. So, for example, the charger and the trap, electrostatic trap, the condition of the electronics and the internal insulators are monitored. So we know if something is going wrong, we get an error or warning first, and then error, so we can prepare for maintenance, or we can do repairs if needed. In addition, we provide maintenance counter if you want to do some adaptive maintenance cycles. Typically, in the applications from emission measurement to ambient, we have about 1 year maintenance interval, often much more than that. Externally, we only require filtered air, clean filtered air at quite modest pressure, then control for the heater, and 5-volt power supply for the sensor. The current draw is about 100 milliamps, so it's a very low power system. And there's a quite simple data interface for the sensor, so it's easy to integrate in different systems. So to get from just current of the particles to actual particle number concentration, we need to know the flow through the instrument and also the particle size. So since we know how the charger works, we know how many charges per particle there are, but we need to know the particle size, and this is being done with our advanced measurement algorithm. So we change the voltage in the ion trap. So we capture some of the small particles, and based on the change in the signal, we dynamically can compute the particle size and use that information to go from the measured current to real-time live particle number concentration, and then update the particle size information every 200 milliseconds. So it's very fast on this way. So the fastest information is always the particle number, and then we update the particle size a bit slower. It's filtered, but we can get to within the stable particle size within, let's say, 10 seconds of a step change in a depending on application and concentration, of course. So the benefit of this, so it looks like this, so that we have multiple simulations of the device response running in background, and we choose the right one, which means that we get the right particle size and flow information here. There's patent pending on this, and this has proved to be quite an effective system for various applications. We get very fast response. So if we look, for example, emission measurements, we have here 100,000 particles per cubic centimeter, and then sudden switch to zero air, so clean air. We track the change from 95% to 5% final concentration in less than 200 milliseconds. So we can make this to operate very fast. Of course, in ambient applications, we do a bit more filtering to get to these small concentrations, so we have slightly slower response in these applications. This has been tested and certified at METAS, so accredited measurement laboratories. These are the certification results for the PTI measurements, so we can get repeatability. We are within the right bracket for particle number measurement, so we have the concentration or the counting efficiency in the approved range, and the linearity is very good, and also repeatability. We just got our new calibration or testing for ambient measurement, so in the range that these ultrafine particles are relevant, we have pretty good detection efficiency, also around 100%. So this sensor then for ambient application is packaged in Pegasor Airam. It's an ultrafine particle monitor for ambient applications. We can get the same particle number, particle mass for nanoparticles, and long deposited surface area, with the added bonus of particle size, of the median particle size. This is designed to have long lifetime and long maintenance interval. So the total economy of operation is very good, and it's suitable for denser networks than are now used in cities. So maintenance once a year is only necessary. We have good connectivity, so we can provide a full solution with a cloud service, or we can provide interfaces for local collection and even local saving internally of the device. So it works in real time. It's non-collective, so we avoid contaminating of the sensor. So even in high concentrations, we have pretty long maintenance interval. We can go up to years of maintenance-free operation, depending, of course, on the conditions. But for example, in European and especially in Finnish cities, it will go years without any maintenance. There's a lot of self-diagnostics, so the aim is to let the user know if there's something additional to be done in the next yearly maintenance. Naturally, it's weatherproof, and we only have one cable going in. It's an power over Ethernet cable, so it provides both the power and the data interface for the sensor. The heater is used to remove water from the particles to improve the reliability of the results. So we are measuring dry particles. So the strategy for the drying is that our heater is 40 degrees centigrade above the ambient temperature. So for example, now I think we have 9 degrees outside, so the heater is at 49 degrees, and this provides less than 15% relative humidity for very wide temperature range. So it's a very simple and robust solution for drying the particles compared, for example, nothing dryers or something like that. We have very good sensitivity if we just average long enough. So it's not a single particle measurement instrument, but we can get to pretty good sensitivity. And we can go up to very high concentrations. So the sensor is the same as in emission measurement, so we can go up to 100 million particles per cubic centimeter. Well, this is not needed in ambient applications, but for example, around emission sources, you often have that typical particle counting instrumentation will saturate and you miss the parts where you have the worst situations. So we can guarantee that this is not going to happen with this instrument. We have a particle number lower cut at 10 nanometers, and we can get the particle size estimate up to 200 nanometers. The sampling rate is 1 Hertz, but we can save the data with longer saving interval if needed. For example, data storage saving reasons. It's pretty well connected, so you can use the Ethernet. There's internal 4G modem, so you just need to provide a SIM card, and you can have the data online in the cloud easily like that. Then there's a local wireless hub also, so you can get the Modbus data through wireless connection, or you can use the Ethernet cable for that Modbus connection. Or you can provide the Ethernet and still use the cloud portal. There's plenty of options here. Then there's also local saving. So if there are no other way of providing data connection, the device can save the data itself, and then you can go and grab the data later on with the laptop. It's pretty small, so you can install it quite easily on a pole or in a wall, just provided that you can get the power over Ethernet cable to the sensor. So that power is needed at some point. So we can provide a data logger. So it's a very simple application. With the PC, it just logs the data from either from the Wi-Fi or from the Ethernet cable. But there are also plenty of these Modbus loggers available, and many data acquisition systems for ambient monitoring also use Modbus as a protocol. So this is very easy to integrate to other systems also. Our cloud portal collects the data. You can set up alarms or automatic reporting. So this is a pretty powerful tool if you want to have, for example, a network of sensors and then to get reporting and even automated reporting and alarms and from the data. And then there's a local memory option as a backup. From the cloud portal, you can get your own instrumentation groups. You can check the data. You can download the data from there for further analysis, and you can do comparisons here. And like I said, automated reporting and alerts. So in this cloud service, we can provide different user groups and then give different sensor groups for each user, or depending on how you want to divide those. And it's easy to make these grouped graphs. So it's easy to access online wherever you need to. And you can also get the diagnostics. So for example, you could set up alerts for diagnostic values. So if you have error in the system, you can immediately get an alert if needed. Okay, and it's pretty well suited for multi-sensor networks. So it's a pretty good tool for that. And as an example here, I mentioned about the high concentrations. This is from a European airport. We have concentrations of more than 1 million close to the airport. But when there is less traffic, we drop to less than 1,000 particles. So the dynamics here is pretty difficult for many instruments. But this is one of the, at least for me, interesting applications so that we can cover the whole range with a single instrument, no dilution needed. And the changes here are quite fast. So this is one of the most difficult applications, but we have seen pretty good results compared with the CPC. Then there are units in Helsinki. Helsinki Environmental Authority, they report LDSA for the public, and they also have particle number monitoring, and these are available for the public. These are of the older cabinet model, but there has been units running there for quite some time now. And this is test data from Helsinki. So just a minute. So we have a comparison between two different CPCs or condensation particle counters, one with a slightly higher cut point and one with slightly lower. So we see that the Airam counts roughly between these two units. So we are quite happy with the performance, even at these low particle size conditions. And we get pretty good sensitivity. So we did, during a campaign, we did filter testing. So we just added HEPA filter in front of the inlet, and we can see that there's 100. So we can get much less than 100 particles per cc zero reading here. So that's a pretty good result for ambient measurement. The correlation between the CPCs with low cut CPCs is it's good. There's the difficulty for ultrafine particle measurement is that especially in here, it's close to a busy road. So any difference in the sampling location, for example, can cause some difference in the reading. So I'm pretty happy with this kind of correlation. Then there's a measurement station in Tampere. They also report measurements from Pegasor units, and this is used in parallel with PM2.5 measurements, as it's seen that PM2.5 is not capturing especially all of the traffic related emissions. So this is a good added benefit for the city planning and public health awareness. Okay, and even here, this is next to not as busy station as in not as busy road as in Helsinki, but we already also see here that we have pretty high peaks, and the variability here in 1 minute scale is pretty high. So the applications for Airam at this point, it's to be used in parallel with PM2.5 measurement to get more information or information that has been missing so far. It's good for dense real-time monitoring networks, since the ultrafine particles are much more spatially and dynamically variable as, for example, PM2.5. So to get comprehensive picture, it's necessary to have more dense networks, and standalone instrument like this is very easy to implement, as we don't need to have, for example, a container or air-conditioned systems for the device. And especially good application area are these, for example, airports and harbors, where they have very high concentrations locally and intermittently. So every now and then you have, for example, high emitters or events that need to be monitored. Then for city planning, measurement on busy streets, residential areas, for example, biomass burning, if you have saunas or fireplaces in some areas. And then interesting application is also construction and mining sites, where there's often activities that produce a lot of particles, and, for example, the emission control on the construction equipment may not be as high quality as in, for example, city buses. So these could be pollution hotspots. So the benefits here, it's pretty robust system. So it's meant for real-time monitoring in long term. And that's it does the measurement down to 10 nanometers. It requires no operating liquids, no filters to continually change, like in mass collection methods. We have everything in one cable, power and data. It's near silent. There's a very silent pump here, and so it's easy to install even close to residential areas, or even in the wall of apartments. So that opens up more installation spots. The price is reasonable, and we have good availability here. And on the user side, the maintenance needs are very low, since there's no or the contamination is very slow on the sensor. And we have several data options available, from just a single sensor to a network of sensors. So it's easy to integrate in data acquisition systems. Then a couple of words about the maintenance. So typically once per year, inspection and short maintenance. So the main filter change, inlet mesh cleaning. So these are operations that can be done on site, so no need to take it out for maintenance. And then approximately, depending on conditions, every 4 years, an extended service where the sensor needs cleaning, and then calibration service is recommended. The package contains the sensor itself, hardware for fixing the unit or getting it installed, calibration certificate, cable, and the power and data unit. So we have a double layer casing here to take care of cooling of the system. So in hot days it needs some cooling, and the cooling air is taken in down here, pulled through a filter, and then distributed through this casing. We have one spot for connector, and the installation hardware can be locked, so this will not be taken out of the wall without heavier tools, and also the maintenance hatch here is closed with a lock knob. So when you need to do maintenance, you just open the lock knob, and then the main filter is accessible right away. And for further maintenance, you can slide out the full equipment bay, so nothing is connected to the frame, so you have easy access to all of the parts. You have the sensor and the pump filter that are the main extended service need parts, and all the auxiliaries, and it's an easy package to do a service on. On the bottom panel we have the Wi-Fi access password and information, so it's easy to get to do setup for the modem. We have the inlet, outlet, and then the data connection, plus the USB connection for local data acquisition. There are some antennas for Wi-Fi and 4G, and a status LED. So if you do a field maintenance, and when you get it back online, it's easy to check that everything is all right, and then you can close the hatch and then be on your way for the next maintenance task. The power and data unit is used to feed the data and power, but also access the data through a PC or connect to data acquisition system. So it takes roughly all mains power voltages that are available, and it feeds the required power to the unit. So the setup is easy. Just fix the installation gear, set up the or lift the unit on the fixture, and then either screw it in or lock it in place with the lock, and then connect the cabling. Everything is labeled, so it's an easy way to have a functional system in a short time. The modem is included. There's a good setup guide for this. I'm not going through all of these possible ways how to set up, but I'm sure everyone will find a suitable way to connect the sensor either through wired or one of the two wireless ways through Modbus or with the cloud service. So I'm sure everyone will find a way to have the data in their use. So as a quick wrap up, we provide the electrical detection technology that is robust, real-time, and has wide dynamic range to measure emissions and air quality with the same technology for all concentrations and environments. So this forms a pretty powerful way of measuring and then controlling emissions, since we can use the same system or the same technology to measure emissions from an engine and exposure in ambient air. Okay, thank you.